Okay. Well, I would like to join all the previous speakers in thanking organizers of the conference for their terrific work. And also, as Alex mentioned, I've been here already for a few weeks as a part of the workshop. And indeed, the whole coordination was outstanding, and also hospitality from KITP and accommodation was phenomenal. So my name is Dmitry Baranov. I'm from Lund University. And today I'll tell you again two stories, which seems to be a trend, about collective effects in Perovskite nanocrystal superlattices, one about X-ray diffraction and another about photoluminescence. The first story is more or less has an end. The second story is open, and I think it would perfectly fit the what's next theme of the conference. So the history of colloidal semiconductor nanocrystals is very rich, and I'm just showing here one specific node related to the luminescent colloidal particles to highlight that over the past several decades, enormous progress has been made in their synthesis and optimization of light emitting properties. And oftentimes it's been driven with the promise of the future where we will utilize the quantum phenomena of these materials. And this remarkable progress is manifested, for example, in the existing technology of QLED TVs. However, recently a new player emerged on this field, which is that of perovskite nanocrystals, which in a, I would say, remarkable time achieved something like superfluorescence, so a macroscopic quantum phenomenon. So if you think that in, let's say, 3-4 years, such an effect has been realized in colloidal nanocrystals, while in the 4 decades it has been very elusive in the 2-6 semiconductors, raises question: is it specific to the material or comes from the superstructure? And is a very interesting question. So what are these lead halide perovskite nanocrystals? For those who don't know, they are typically come as nanocubes, which reflect the crystalline structure of the underlying material. And they have a nice absorption spectrum with a discrete electronic transition. They are bright emitters. So there are a couple things which are unique to them. First is their electronic structure, such that, for example, they have a bright state at low temperature with a transition to the lower energy dark state inhibited, in contrast with the 2-6 nanoparticles. Another interesting property is that they form polarons after photoexcitation, meaning that electron-hole pairs are polarize their immediate environment, and in that way are being stabilized, and that's what underlies, for example, remarkable efficiency of perovskite solar cells, since these are ionic semiconductors and not covalent. So now, artificial atoms and collective effects. So this is a figure 1 from the overleaf paper, and I think it captures the essence of the workshop and the conference, where we think of nanocrystals as artificial atoms, which then let us build artificial solids. So I'll be talking about this last part, artificial solids, and in my case, I'll start with X-ray diffraction. So familiar picture of the Bragg's law, which happens on the angstrom scale, where the atoms, which are arranged in the planes, scatter incoming X-rays, and then, because of the phase matching, produce constructive interference. So you take a nanocrystal, it's made of atoms, it gives you a diffraction pattern. Then one might ask or wonder what happens if you now build a crystal out of nanocrystals, and then would they diffract collectively? One answer is that yes, they would, as we saw in many small angle scattering experiments, but then would there be also some orientational order and more interesting effects? So materials or nanoparticles I'll be talking about are the cesium lead bromide 3 nanocubes, which we make by the hot injection method by combining lead bromide with a cesium oleate in the presence of other surfactants. So they appear as these fairly uniform cubes in transmission electron microscopy images. The small black spots you see are the lead zero, which is formed as a result of the beam damage. Then they have a quite interesting and dynamic surface chemistry. So first we started making this, making self-assembly by solvent removal. In essence, we dispersed perovskite nanocubes in hexane, a good solvent, deposited it on the surface of perfluorodecaline, solvent which is miscible with hexane, but a bad solvent for nanocrystals. Hexane diffused, producing these cuboidal objects, which turned out to be superlattices that can be dried in a cluster or further dispersed in another solvent. Then we looked at their topology to convince ourselves that they are three-dimensional objects. And indeed, by this method, we can make quite big superlattices or big assemblies with estimated 10 to the 11 nanocrystals inside. So one can make large superlattices in that way, but also one can make small ones, for example, like this supercrystal here. And we looked at, when we looked at wide-angle electron diffraction, we noticed something which we thought is remarkable, is that instead of diffraction arcs that one would expect, we saw pretty much very narrow arcs, almost spots, that corresponds to quite a remarkable crystallographic orientation of nanocubes with respect to each other. And this is more or less what we expected to see based on our intuition developed on cadmium selenide nanocrystal literature published in prior years. So in a wide angle, we were expecting to see arcs, and we saw dots, almost dots. So to characterize it further, we moved to assembly by solvent evaporation. So simply depositing dispersion of nanoparticles in tetrachloroethylene onto silicon wafers, tuning concentration to go from these isolated supercrystals to the superlattice films, as we call them. And then we performed wide-angle X-ray diffraction, because in this case you look at a pretty much macroscopic sample, you have high signal, and here's what we found. So when we looked at the control sample, that is a nanocrystal powder, we saw, as expected, reflections coming from the Bragg peaks of the orthorhombic perovskite lattice. When we repeated this on one of these superlattice samples, whether film or isolated, we saw a very different pattern. So in the low angle region, peaks as expected from the superstructure. Then we lost some of the reflections due to preferential orientation. And the first Bragg peak, moreover, showed a peculiar fine structure. Again, this was something very different than what we were used to based on cadmium selenide. For example, here's data from one of the Chris Murray papers, where once they form a FCC superlattice of cadmium selenide, at low angle you see superlattice reflections, but at high angles you see only preferred orientation effect without any fine structure on the Bragg peaks. So what is the origin of this fine structure? It turns out it's what's called a multilayer diffraction. So nanocrystals are well packed, and then the second superlattice periodicity produces constructive interference of X-rays, similar to very thin epitaxial multilayer films. So first we could do some phenomenological analysis and simply fit the diffraction peaks following a rearranged Bragg's law. So we replot this diffraction peak on a logarithmic scale, fit it as a sum of contributions from disordered nanocrystals and then this multilayer reflections, fit it following the Bragg's law, and then we can extract lambda, which is in this case, superlattice constant or center-to-center nanocrystal periodicity, which agreed fairly well with the center-to-center distance measured in TM on the nanocrystal monolayers. So immediately, this diagnostic was useful for something like studying how superlattices dry under vacuum. Because right after self-assembly, which is done under ambient pressure, the film of superlattices is still wet. It's kind of like a wet bread, if you will. So if you put it under vacuum and start collecting diffraction patterns, you see that the shape of this peak evolves over time, over about 90 minutes, hour and a half. And here's shown superposition of what the peak looked before like and what it looked like after. And then by fitting, by performing the fit like I showed before, we can kind of track contraction of the superlattice over time. And the magnitude of the contraction is approximately compatible with the size of the solvent molecule tetrachloroethylene. So we were content with explaining it as an effect of simply evaporating the residual solvent. So basically drying our bread into a dry bread. Over time, we improved our understanding of this effect. So here's its physical picture shown diagrammatically. So incident X-rays are first diffracted by the atomic planes of each nanocrystal, producing a Bragg peak at a certain Q position, which is broadened due to the finite size effect. And then, because of the secondary periodicity lambda, there is an additional phase shift that produces secondary interference with the spacing according to the superlattice constant. And then, as a result, you have this peculiar split profile. And Stefano Tosa, PhD student who recently graduated, was instrumental in developing this picture and helping us to harvest all its potential. So by having this qualitative understanding of the phenomenon, we developed a quantitative model, and which allowed us to actually take this X-ray data and then extract basically as much as we can about our nanoparticles. So, for instance, we can set or feed the nanocrystal size, which would produce this broad Bragg peak. Then we can add a parameter of superlattice periodicity, which would then perform a convolution of this superlattice peaks with a broad peak, and will produce something like that, which doesn't look anything like experiment, shown in blue, for the reason because it's way too perfect. There's always some disorder. So next we can add simply Gaussian disorder of this superlattice periodicity, and now pretty much capture the shape of the experimental diffraction peak, and finally add the size distribution, also Gaussian, and then produce an adequate fit. So as a result, we can quantify structural parameters of superlattices, both for nanocubes and nanoplatelets. What is it useful for? We can track changes in the superlattices as we heat it. For instance, we performed an experiment where we heat superlattices with the 25-degree steps, and we saw that superlattices contract and get better ordered as a result of that. So we produced and shared it, the whole fitting procedure and experimental data as an open source code, which you can find in the supporting information of these papers or on the different depositories, as we think it might be a valuable tool for the people working with this system. So next, few more words. So comparison with model. So Alex yesterday gave a very nice talk where he explained the model of the cubes packing. So, and then I thought, okay, let's compare the results we obtained using diffraction with the formulas and models which have been recently published by Alex in ECS Nano. So first, looking at nanocube superlights with olyelamine, olyelamonium ligands. In this case, we don't know the surface coverage. We just didn't bother to quantify it. What we know is that the way we treated our nanocrystals empirically would probably result in a high surface coverage percentage. So in this case, the predictions of two models, one which is just hard surfaces with a polymer brush in between, and the second one, so sort of a soft nanocubes. So in this case, I would imagine if we knew the experimental surface coverage, we would land somewhere in this range, which would give a good agreement. But this is a hypothetical. For example, for the case of platelets, however, we knew the surface coverage quite well, and we knew the ligand, and it lands us exactly on this black line, which is the case for the two hard surfaces, where the surface length is much larger than the ligand length. So you might say, okay, this is just one data point for olyelamine, but we also had data for octylamine, C18, and also knew its surface coverage, and again, we landed right exactly on this line. So I would say in this case, it was a nice illustration how our method was in agreement with the theory, which was published independently, essentially. So what else can we do with this diffraction? Well, we can predict diffraction patterns. So on the left are shown TM images of different colloidal nanoparticles which are produced with sufficient uniformity to form superlattices. Cesium-4 lead bromide 6, lead sulfide, nanosheets of lead sulfide, and nanoplatelets of perovskite. So by applying the routine we wrote to feed the data, we can use it to calculate diffraction patterns for various hypothetical well-ordered superlattices. So if we try to assemble these probably quasi-spherical nanoparticles, and depending on the geometry they assemble in, we might distinguish them or perhaps not. Here's a case for the different thickness of cadmium selenide nanoplatelets in a zinc blende crystal structure. We tried, but we couldn't get nice assemblies, probably because these platelets are quite flexible and are susceptible to different twists and distortions. And then for some binary structures, for cesium lead bromide nanosheets and lead sulfide nanosheets, alternated or randomly mixed, same for the nanocubes. So this some predictive power to that. Okay, so now I'm going to go to the second part of the story. So the theme is, again, basically common theme is interference. So I spoke about constructive interference of scattered X-rays, which results in this cooperative effect. Now, the nanocrystals in these superlattices are semiconductor luminescent nanocrystals, which can be excited by, for example, blue light, and then emit a photon, okay? So if we think of each of these nanocubes as essentially an oscillator with its own amplitude, frequency, and a phase, then in the superlattice we will have many of them, let's say n. Now let's imagine that all of them are exactly identical. So if they are artificial atoms, so all atoms, let's say, are identical. So in this case, all the frequencies will be identical, amplitudes, and there will be no phase shift. So in this case, the total amplitude will be just simply a sum of the individual amplitude, and the intensity, which is a square of the amplitude, will be proportional to the n squared, to the square numbers of emitting particles. And this is this square intensity of the, in this case it would be radiative decay, is essentially at the core of this superfluorescence or superradiance phenomenon. So let's look at the state of the art. So experiments on superfluorescence in perovskite. So it's the field, I would say, was opened by the work from Maxim's group in 2018, where they observed interesting peculiar redshifts at low temperature in the nanocrystal superlattices of cesium lead bromide 3 with oscillating and very fast decays in time domain. So since then, quite a few papers appeared. Sorry for the overwhelming slide. You don't need to take a screenshot because you can look up these references at the recording. But if anything, it kind of indicates what's next, right? Because you would expect that there would be some sort of further continuing growth as more groups join into studying this phenomenon. Some remarkable findings you can find, for example, last year, superfluorescence has been reported in a perovskite thin film at 300 kelvins, and then several works on various nanocrystals and superlattices. So in the following, what I want to talk about is what is this effect and perhaps how to achieve it, which I, let's say, leave for an open question. So what is this effect? So as far as I can tell, its history goes back to the mid-50s, to the influential theoretical paper by Dicke from MIT. So this appeared in the era between maser and laser. So when also active progress was made in the nuclear magnetic resonance, so the Dicke thought of an ensemble of two-level systems which are confined to the volume much smaller than a wavelength of light. And then after initial excitation, coherent excitation, all these dipoles are in phase and they produce this intense burst of light, which is called superradiant by Dicke in this paper, with a peak intensity proportional to the square of the dipoles. So essentially it's similar to the physical picture I described before. So the first experiment claiming this effect appeared in 1972. It was on the hydrogen fluoride gas. So it was a low pressure cell. So how low pressure? So this is the number density, 10 to the 13 per centimeter cubic. This is roughly 40 molecules of hydrogen fluoride per cubic micrometer of space. So you can imagine that the molecules are really far apart. The reason for that is that you want to avoid any collisional quenching of the excitation and any as a source of decoherence. Now, it was observed on this infrared transition. So even though there are few particles per cubic micron of space, because the emission wavelength is so long, it kind of includes many, many molecules. And what they observed essentially was that in the time signal of this peculiar emission, after pump there was a delay of some microseconds, which is then ended with a burst of radiation coming out in this oscillating manner. Moreover, the peak intensity of the signal was proportional to the square of the number of molecules. In this case, it's a pressure. It's plotted on the x-axis. It's a pressure squared. So this is pretty convincing square dependence of the intensity. So from this work, this influential cartoon have emerged where they illustrated excitation pulse, so very short excitation pump. Then what happens in case of standard emission? There is a radiative decay with a uniform intensity distribution. And this is what happens in case of superradiance, where you have this burst of radiation, and then it's directional. So it's directed along the direction of the highest concentration of emitters. In this case, cigar-shaped sample, so it's emitted at the ends of the cell. So some conditions from this experiment or some rules one can pick up is that all emitters should be identical, and there should be, let's say, any decoherent sources shall be minimized, for example, by low pressure. Next, stimulated by this experiment, Bonifacio and Luggiato in Italy came up with a paper where they say, wait a second, this is not the Dicke case, it's actually something different, it's a superfluorescence, because after excitation you have all dipoles misoriented, let's say, and it takes some time to build up this coherence, hence the delay, and then once it spontaneously builds up, you have this burst of emitted light. Then subsequently, the experiment with the superfluorescence, for example, was repeated on the sodium vapor by a group of Serge Haroche in France. Again, they used the sample cell, elongated sample cell, dilute vapor, much lower number density. Again, now also excited, so this delayed emission and its dependence on the excitation intensity, and again, the pulse height, so the peak intensity was proportional to the excitation intensity squared as expected. So this is kind of a historical overview about what is this superfluorescence phenomenon. So in our efforts, we so far attempted twice to look for superfluorescence. In the first case, we looked at in collaboration with a group in Lecce, we looked at the freshly made superlattices of perovskite nanocubes. When we cooled them down, we didn't see appearance any additional features, and when we tried to check whether we see anything with increasing laser fluence, we basically just photo damaged our superlattices. However, what we did find is that we learned that over time, the superlattices undergo a chemical transformation, nanocrystals coalesce, and then their emission red shifts, and then they become more stable to the increased excitation fluence. In either case, the intensity of the signal of the peak intensity versus fluence was had a quadratic dependence. So these experiments we did in collaboration, as I mentioned, in Lecce. It's the south of Italy, humid and warm, not a good environment for perovskites, so they aggregate. We learned that, okay? Later, we collaborated with another group, this time in Brescia, so it's in north of Italy. It is colder and drier, okay? We changed nanocrystals. We used particles with different surface passivation, compared disordered film with a superlattice film, and in the samples which have been aged like a good wine for 90 days, I think good wine for 90 days, maybe not, we saw appearance of the new resonance in the transient reflectance data at low temperature, something similar to what was reported in 2018 from Zurich group. And then as a function of excitation intensity, we started seeing some superlinear intensity dependence. And then we sort of figuring out how to interpret it and what exactly constitutes an evidence for cooperative effect versus multi-exciton or other processes, which of course happen in semiconductor nanocrystals. So, and now I move to Lund, which is colder, darker, and drier. So I hope the third time will be a charm. So important open questions, which I listed here, concern 4 categories. So first is the time scales, because we're talking about nanocrystals, which are not two-level systems. They have more sophisticated electronic energy structure, as well as the not lifetimes, but time scales of radiative decay versus decoherence versus the characteristics time scale of cooperative emission. Second question is that of disorder. So as previous speaker mentioned, even though, for example, lead sulfide, all particles are connected, but each of them is slightly different. Same applies to these samples. So energy disorder, positional disorder, as well as orientation, all might play a role or not in this cooperative optical effect. Next, exact nature of interactions which you need to achieve this phenomenon, or some of its variation in these assemblies. If you're thinking about the superfluorescence being caused by dipole-dipole interactions, it means that you want to keep your emitters close to each other, but maybe not too close. So there is no, and then you kind of wonder what happens with the competition with Forster energy transfer and so on. And then structure, whether these effects are intrinsic to perovskites as a material, since there are reports of something similar in thin films, or they arise from the superlattice structure of the sample, and whether superlattice is necessary and which exact one, monocomponent, binary, and with what exact arrangement of the components. So I think, I hope by the next time there is this workshop and conference again here, we will make progress as a community on these topics. So with that, I want to thank you for your attention, various funding sources and organizations that have been supporting my work, and I'll be happy to take questions. Thank you.
Sasha. Dima, first question about this cubic shape perovskite nanocrystal. We know that they are not cubic. How did you take into account?
So yes, that's a good point. We don't know how exactly cubic they are and whether there is additional distribution of sizes in the sample. So so for diffraction experiments, that didn't seem to play a role because there was some size distribution, and we treated it as a kind of a uniform size distribution, as a uniform cubes. But in fact, in a real sample, if you're thinking about size distribution of cubes, it can be cubes with a uniform edge length, or it can be something like parallelepipeds with a one extra plane on one side and so on. So answer is, I don't know. Moreover, just to say that, so since the perovskite nanocrystals emerged, there's been multiple syntheses of high quality particles. Some of them seem to be more cubic than the others based on different studies. For example, I know that I think systematically from Maxim's group with some sophisticated small angle scattering, they determined that particles are indeed slightly elongated. Yeah. So in some other works with high resolution microscopy, other groups claimed and other synthesis particles are more cubic. So there is also this dimension to your question.
And want to add some comment about superradiance. It would be useful for people to know that in order to observe Dicke state, coupling between particles should be larger than inhomogeneous and homogeneous Baranov.
Right.
So these two papers, first, she reported really serious question about what that is.
But the broadening at zero temperature could be very small. And then, oh, sorry, no, I'm just.
So I mean, yes, I think this is a very, very good point. Yes.
Okay, so I have a question, which is that what is the maximum temperature at which superfluorescence still exists as a coherent effect? Yeah, I mean, we've had this a little bit, this discussion.
Okay, so hydrogen fluoride, sodium atoms, experiments at room temperature. Sodium even, I think, might be heated to produce enough concentration of the vapor. So in principle, but those are atoms. You can, if you can manage, in nanocrystals, you would have, of course, phonons once you start warming them up, and electron-phonon coupling. I don't think there is a material where it does not exist. So maybe Aaron.
I actually do want to touch upon this point. There's a big difference, and it goes back to the previous talk and maybe to other talks, who call these particles artificial atoms, which they're not. They're artificial atoms if we think about their spectroscopy. But any other property, they have internal degrees of freedom. That makes them very different. There may be molecules more than atoms. But in many ways, they're also very different than molecules. And in one way is coupling regime is very different. Coupling to the phonon regimes is very different. And also density of states is very different, density of excitations. And you can actually play around with these three by choosing the right material, the right geometry to actually enhance superradiance where you wouldn't think it would exist if you just had a two-level system. So it's a more complicated problem, I'd say.
Yeah, I mean.
But interesting at the nanoscale because it brings in things that we haven't thought about in the context of superradiance in atoms.
I think about artificial atoms notion, at least, I guess it's fair to say that it's artificial atoms used broadly with two flavors. Artificial atoms speaking of electronic structure, and the artificial atoms when you make materials out of them. So in that sense, I think it still maybe have some viability as a term.
Okay. Dmitry.
Yeah, thank you. I recall it was in one of the latest papers, Maxim's lab measured superfluorescence on different superlattices, like including binary, ternary. Could you summarize their findings? Did they see any relations?
I don't think there's been some unifying physical picture explaining how superlattice structure connects to the effects they observed, because in some cases they observed redshift, so of this new superfluorescent peak. For other superlattices, they saw a blue shift of the superfluorescent peak. So I think, yeah, I don't think I can speak about the current picture in their materials.
Thank you.
I mean, since I am one of the authors of this paper, I will say that there were 3 superlattices, and 2 of them gave superfluorescence, which is AbO3 and Ab2, and the third one, which is sodium chlorine, did not, you know. So I've been talking to Aaron, and Aaron says that it is a very easy problem to predict which ones are superfluorescent, but so far we haven't moved forward. I don't know if you want to add something.
I didn't hear the first part.
Oh, well, the question is that how easy is to predict which lattice makes superfluorescent and which won't, basically. So which one?
I didn't say that something. I'd say it's something that is easy to answer with the model.
Basically, I mean, what we had, I will repeat a little bit more the discussion. The discussion is that in those superlattices where there is contact between the perovskites, Aaron expects that there would be superfluorescence.
You mean contact? No, then I would expect it would be, if you hybridize the particles, it would ruin completely superfluorescence, I feel. It makes it.
In sodium chlorine, for example, the cubes are separated by the spherical nanoparticles, and they are fairly separated. So in that case, it seems reasonable that superfluorescence is lost. So this is kind of
That's because of the separation. I mean, in
basically-
superfluorescence in atoms, it goes by dipole times the overlap of densities of states. So as Sasha said, if you have inhomogeneities that overlap, you're in trouble. If you have homogeneities that kill that, you're in trouble. But you're in a different regime in nanoparticles, and through the assemblies, you can get a better control of maybe separation, which is very hard in atoms. And also maybe through the material composition, you can get control of the density of states, which also enhances superfluorescence. So, but I didn't say it's an easy problem.
No, it's not an easy problem. Well, it's not difficult. Okay. So, if there are no other questions, there are a couple of things that we should mention. We are going to have lunch now. Then after lunch, we will have the poster session. And then after the poster session, we will come back here and we will have 2 more talks. And then we will have 2 more talks and we'll have a lot of fun. And then we will have dinner also here. Yes, Michael? So yeah, I mean, so that's the plan. So we have, we have a lot of time of community together. Yeah. And let's hope to have very good discussions. So thank you, Dmitry.